Good afternoon, colleagues. I would like to introduce you to the radiation embrittlement and hardening of Wwer 1000 type RPV base material. Here is the content of my presentation. Firstly, I will introduce you to the RPV radiation embrittlement. Then I will describe briefly the method for the analysis the data. And then I will show you the results for chip impact testing data, tensile testing data, and T0. After that, conclusion will be made. So here you can see how radiation embrittlement acts. This is a Wwer 1000 materials. Initial condition and radiation condition. We can see that the hardening effect, which consists in ultimate stress and yield stress increasing. Also, here you can see the Cherpiv curve shift and fracture toughness, T0 fracture toughness shift, the initial state and the radiation state. These effects affect to the RPV integrity assessment that must be taken into account to the lifetime extension, so here is the Wwer 1000 reactor characterizations, the materials, base material and weld material, mechanical properties and chemical composition. For this reactor, according to the design, 4 types of spacement applied: tensile spacements, Cherpiv spacement, fracture toughness, and low cycle fatigue. The most valuable spacement is Cherpiv spacement, since based on these results, lifetime assessment made of RPV. So in Western countries, that's Japan and Korea, radiation embrittlement trend equation curves takes into account chemical composition effect. It is well known from microstructural investigations that copper, nickel, mangan, and silicon have effect to the radiation embrittlement and hardening. But until now, in Wwer countries, there is no chemical composition incorporated to the radiation embrittlement assessment. So the main goal of this work is to define chemical composition effect to the Wwer 1000 RPV base metal. So in order to achieve this goal, we develop a simple engineering method. The goals of the methods are listed here. The main idea of the method is to provide fast and repeatable homogeneous results of calculations of solving of system of equation and the convergence of it. Here you can see the base curves, which we use for approximate transition temperature shift, yield stress, and T0 shift without chemical composition. And in order to define quantitatively define level of impact of each chemical element, we modify radiation embrittlement and hardening coefficient incorporated to them chemical element. So and how to get back? Sorry. And based on the comparison of the correlation characteristics and between pures with chemical composition and without, and based on the data scatter in terms of standard deviation. And based on the comparison of this characteristic, we will make decision about chemical element, each chemical element itself in terms of effect, whether effect or not effect to the radiation embrittlement and hardening. This we apply two criteria in order to make decision. First one is from 5 to 10% impact if the chemical element or synergetic effect lies between this region. So this element should be considered fused, and if this element affects more than 10%, then this element should be included to the formula of hardening or embrittlement. The same criteria we use for the synergetic effect, but quite different equations. In order to make conclusion regarding synergy, two trend equation compared. First one with two chemical elements itself as additive influence to the embrittlement or hardening, and the second one is with synergy. The multiplication of these elements shows the synergy. So and the final decision making regarding embrittlement trend equation will be made based on the deep analysis with all elements and all synergy, including them to the equation or excluding, and comparing level of improvement and data scatter. For instance, if we have two equations, one I would say more precise, and if the data scatter very close, between these curves, then we can easily exclude this synergy. So now we have this slide shows the transition temperature data for Ukrainian Wwer 1000 reactor-based materials and level of impact of each chemical element. And we, according to our criteria, the most impact on embrittlement have phosphor, cobalt, arsen, sulfur, and copper. Next, we define common influence of these elements. Then we define effect. We investigated the possible synergy between these elements, and we obtained that only arsenicum and silicon should be further investigated, and the cobalt and sulfur also should be considered. This slide shows the deeper analysis for radiation embrittlement coefficient finalization, and we stopped on the three the most well-known from the literature elements, because from the engineering point of view, if we compare complicated equation and simple equation, there is no reason to use this complicated equation, because moreover these elements are well known as effective from the microstructural investigations and from mechanical investigation in 70s and 80s years of last century. So here is the results for the radiation handling of the Wwer 1000 RPV base material and final equation for determination of the hardening. I must say that hardening is also important since for some cases in Ukraine we need to perform elastic plastic RPV integrity assessment. I mean elastic plastic G integral calculations, which with taking into account real yield stress. So and for those forgings and zones of base materials which were not presented in surrounding specimens, this equation should be very relevant. And last but I think not least in future, here are the results for reference temperature, radiation embrittlement trend equation. So as for now, reference temperature have been not used in practice for RPV integrity assessment, but as you may know, in world there are a lot of works, investigations in order to incorporate it to the normative documents and standards for reactor technology. In order to save time, I will not give conclusions. You can see that. Thank you for attention.